Uh, okay, so let's continue our discussion about the client and the cloud. Hopefully, today network is working better, so I'll be able to show some demonstrations that we missed yesterday. First one was about fetch climate and visualization as a research tool. I said that to better depict some interesting features in the data, scientists interactively tune some controls, like you tune a radio receiver to catch proper wave. So let's see how this works, the fetch climate. Fetch climate is a service developed with Microsoft Research together with our laboratory. It provides scientists with climate data. It is available, so you can try to go to fetchclimate2.cloudapp.net. Okay, so this is a typical client application that allows user to formulate request for the data. Now I am getting array of 100 per 100 cells with climate data. I think my climate data will be relative humidity. And I want this data in the first decade of 21st century, monthly average. Then let's request data. Yesterday, we stuck on the receiving phase. Yeah. Now it works. So, this is data. Here you see a palette that shows humidity from percentage from 90%, 20%, which is a very arid areas. And you can explore the data by moving slider. This, as you move slider, something changes, but not very significant. And probably this is not what we want. So the first thing is to control the palette. Palettes are very important tools of visualization. By choosing correct palette, you can display data in completely and percept data completely different way. This one is better, and this palette has a very interesting feature. It has white in the middle of the interval, greenish color on lower part, and some kind of magenta on the upper part. So with this palette, you can clearly see where on the map data is below average humidity and where is above. And new knowledge is gained. I can increase transparency. And with this palette, you see how humidity changes through the year in much clearer way. But this is not all what can be done just with palette, with functions that transform color, values into color. I can make palette discrete with some constant color, and if I choose, let's say, 4 or 5 bands, I will immediately paint the region in a 5 classes, divide visually divide region in the 5 classes of humidity, from very humid to very arid. This is done with only one visualization. So probably this is what I want, but the next thing that I want to discover is what is the most arid area. Where is the, what point is the most arid in entire year? Here I can switch to another type of visualization. And here you can see this plot. This is a month. And these are minimal value. These are maximum value all around the map. And this is the current selected month. So I can quite easily, visually determine the most arid point. This happens in June. And I see the region which is the most arid. To finally determine the point here, I can put a thing called probe, and as I move the thing, a third graph is moving in this window, allowing me to probe for the most humid point, and probably here it is, almost here. So we find it. This was done by tools of visual exploration. And one very important finding from this is the palette is a very powerful tool. So if your client receives some data from the server, it's better that it receive a numerical value, so you can interactively change palette without asking server, please redraw the same data but with different palette. Because clients right now are quite powerful computers, even programs that are running inside browser, I mean JavaScript program, they have a quite good computational possibilities, at least enough to paint data with palette. Okay, so this is fetch climate. How fetch climate works from inside we'll discuss a bit later. Let's get back to our data. So, yesterday we stopped on the idea of chunked arrays. I have 2 data sets. This data set is available, and let's verify this. Yesterday we were unsuccessful. And this is indices of chunk 000 windows.net. Here it is. Browser suggests me to download a piece of data which size is exactly 2 megabytes. So chunks are there. I hope chunks for second data set, WorldClim, are also there. The difference is WorldClim 000 Windows.net, sorry, not com. Here it is. It's funny that for this chunk, the Internet Explorer doesn't suggest to download it, but instead just show data inside. But it's here. These chunks are just a plain binary chunks of data. And if I just give you this URI, it will be useless, because you don't know how many chunks are, how data is located in the chunks, and what is the meaning of the data inside these chunks. So each chunk is an array of 2-bit integers holding temperature. How we can convert this temperature to degrees Celsius? The answer to this question is maybe different for each data set. For this sample data set, the formula is here. This constant should be familiar to you. First one, what is this? This is constant to convert from Kelvin to Celsius. This is a shift, and this is a scale. This is, so the second two terms are encoded into this data. So we need to put a temperature into 16-bit integer. 16-bit occupies smaller amounts than, let's say, floating point numbers, and this is important. 2 gigabytes versus 4 gigabytes is still a significant difference even nowadays. So in this data set, the values was scaled and shifted to accommodate in the region from 1 to 65,000 in the most comfortable way, without maximum loss of precision. So we have this number of chunks, and this pseudocode describes how to extract individual value from the chunk. Second data set is volt-clean monthly precipitation. So it has quite a good spatial resolution, about 1 square kilometer on the equator. First index is month, second index is latitude, third index is longitude. So the size of the chunk is 4 megabytes, and please notice that form of the chunk is different. This chunk has only one element height, and this element corresponds to the time. The size of entire data set is 19 gigabytes, and so far, I just checked, I have uploaded only the first slice. So E here works if E equals to 0. But the process is going on, and I believe soon we'll have all 19 gigabytes uploaded. As you may see, I just put this URL in browser and get the data. The only thing I used was Internet Explorer. And I have no services deployed in the cloud, just blob storage, which is quite cheap. This is good. Then we need to build an application that extracts data and visualizes it in certain manner. I have built a simple application. I have put it to the archive with URL here, but we can look at the source code right now. What it does, it extracts a first slice of time from the NCEP dataset and plots isolines over the map. Let's see how it works, and hopefully it will work too. We can estimate how many data is loaded if we want to show one slice of the time for the NCEP dataset. The data size is 3 chunks per latitude, 5 chunks per longitude, and 90 chunks per time. We are interested in one slice of time, so we will be getting only a single chunk along time axis, and we are getting about 1% of the data, which will be about 60 megabytes of data. This is not very much, but still for wireless network, this may be significant. Let's run the program and see what happens. This is not program, this one. Happens. Please bug. One moment. This will work. So we see a map, and eventually this data will be appearing. Okay, so data is here. It took about 6 to 9 seconds to display the data, and we can look the actual isolines with numbers and see that this data matches the shapes of continents quite good. So this is application that extracts data. It doesn't require any cloud service. It just uses blob storage. What's inside? Oh, inside there is a code which is called getSlice. This code is written in C# code, and I believe you will not have any difficulties working with Azure SDK. The idea is quite simple. Here I create a client for accessing blobs. Please note that in this URI I didn't specify any access keys or any other secret information. On your Azure Trading, you knew that for accessing Azure Storage you need an account key, which is a secret. If someone knew your account key, he can erase data, or which is sometimes worse, he can put his own data to your account. And you may not even notice that, because if there are a lot of data in the account, we just don't care what's inside. And your account can be used for storing and distributing data. It can become quite a big problem if this data is illegal. So keep your account keys safe. Okay. So I made these blobs public, so you don't need any account key. Then I create a reference to containers like directory and set. And then I have a blob object, and for the blob I have an operation which is called download to byte array. This one. Download to byte array. So it's very simple in any other programming language like Python or C++. You can have the similar constructs. And even if you don't have an Azure SDK libraries for your programming language, I'm sure that this programming language supports accessing HTTP resources. And you can access the blob just an HTTP object. that what actually happens inside download to byte array method. A very interesting observation that here we have loop, two nested loops, which extract 15 blobs. And they do this sequentially, which is not very good. Because accessing blob data is an asynchronous operation. You send web request to the blob storage, and after some delay, data starts to flow to your application. And this delay can be, strictly speaking, indeterminate. If you have good network connection, it's very fast. Download blob completes in second or millisecond. If you have bad connection, this may take minutes or even result with error. And I have another interesting application where I compare. I will just open this code. I will compare two approaches for downloading data. In this first part of code, I just download data synchronously. I have this download to byte array method, which is completed just after all the data are loaded. And this part of code uses asynchronous method, which is performed asynchronously. Most programming languages, JavaScript, C#, Java, and many other, have now support for asynchronous operation. And this is a vital feature in today's connected world, because when you address some network service, some network resources, you may return answer, you may get answer in millisecond and second, in a minute, and waiting for the result is not a very good idea. You can do something useful between accessing the resources and getting the result. So almost all asynchronous patterns works in the following manner. You start operation, download to byte array async, and this method in C# interpretation, I return task object, which will be completed somehow, which will be completed eventually. So in the loop, I start 15 tasks, and here I wait for this task to complete. So I start 15 downloads from blobs simultaneously. Let's compare this one. Parallel. As a parallel test. Okay. So each dot is one downloaded blob. When we have 15 dots, we downloaded sequentially all the data for one license. For parallel operation, I don't draw dots. It's not very difficult, but let's see what happened when you use parallel operation. You have 1 2 seconds. And this happens on quite slow wireless connection. Let's try the same experiment in another environment. In a virtual machine located in the cloud, in the same data center with blobs. I have prepared a virtual machine yesterday. This one. their networks works much better. Okay, this is the same application. So here, I have the same executable, absolutely the same, it was just copied, and let's see how access to the data works from the cloud to the cloud. Let's repeat several times for better reproducibility. And the results are quite different. In cloud environment, sequential download of 15 blobs took, let's say, from 1 to 2 seconds, and parallel downloading of blobs took less than a second, and we have almost triple speed up. So if you're downloading data from Azure, I certainly recommend you to use parallel and asynchronous operation. On fast internet connection, you will gain a lot of performance. Okay, so this is about the client. The source code for the client is available, so you can play with it. And here I have two versions of getSlice method, which is in fact an operation that performs a slicing or hyperslapping of the array. This is the core operation that I described yesterday. It extracts one slice from the array. And I have asynchronous operation, getSlice async, which uses async keyword. I won't go into details about async keywords in C# because it's not the subject of our lecture, but I strongly recommend you to go into asynchronous programming. Today it's the best way. So, this was a client written in C#. It was an exe application, and it runs on my computer. What about clients running in the web, like Fetch Client application? They have a significant advantage. They are cross-platform. Because if you use HTML5 and JavaScript, all modern browsers can run your client. And you have your data, your visualization, your service available on Windows to Unix system through the iMacs iPads. As we've seen before, there is absolutely no problem accessing blob from the Internet Explorer. I just put URI and get data. Anyone who tried to program JavaScript these days knew that JavaScript has the ability to access network resources using knowledge called attacks. Asynchronous JavaScript is but there is one problem that hopefully can be solved. Scripts now is not scripts anymore. They are powerful, complex program which compare with their complexity with desktop programs. And because of this, the threat created by programs in the browser is very a lot of complex scripts that does something. And these scripts can't be executed from the internet, so it's always a good point for that. And this happens. That's why scripts running inside browser run inside sandbox. They don't have access to your local file system, that's understandable. And by default, the scripts don't have access to any data that lies outside your domain. I mean, my script, my fetchclimate interface is located in fetchclimate2.cloudapp.net. If I try to access, to get, using Ajax technology, something that lies outside the domain fetchclimate2.cloudapp.net, the browser will prevent me from doing this for the sake of security. And this is a problem because the address of the blob is not in the domain of fetchclimate, and it's certainly not in the domain of your application. You won't deploy your application in the fetchclimate, FC chunked storage, blob core, Windows net, and so on. You'll have your own internet address. The technology which enables JavaScript application to access data in different domains is called CORS, or cross-origin resource sharing. It is quite simple, and it requires to annotate these resources as available for cross-origin sharing. And blobs in the NCEP blobs in this storage account are marked as safe for cross-origin resource sharing. I won't go again into a lot of technical details because you can find all this in documentation. What I need to do is just to run this code. So configure course. This code is performed a single time, and it marks your blob storage as course compatible. And then I can write an application in JavaScript that will show my data, again, without any service. Here it is. Let's try. I don't specify the name of the page, it's page HTML. So this is a browser, an application running in a browser. Page HTML. Here it is. Almost a temperature for almost entire year. You can zoom inside, see some fluctuations of the temperature. And this is a one point in space from a single chunk, which, if you remember structure of NCM dataset, is 1,000 elements, and we have temperature measured 4 times a day, so we have about 250 days on this picture. And if I put this code on my website, maybe Asia website as well, you will be able to access this from any device and see my data. So what's inside this JavaScript application? It looks quite similar to code we have in C#. It's even simpler. So I use XML HTTP request object in JavaScript, and there is one small technical detail. It is called XML HTTP request. So the name says that the result will be XML, and we have just plain binary values inside our chunks. This XML is a bit of legacy, because when this technology starts to emerge, most documents were XML that were fetched. using this technology. Then it appears to be a JSON object, a text files, and finally it is a binary object called array buffer. This line is supported in all modern browsers, but in browsers that are older than probably 1 or 2 years, this won't work, so be careful. And then, when request is completed, again, this is asynchronous operation. Here I start this asynchronous operation, and when operation complete, onload handler is called. I just get the response as an array of 16-bit integers and use the same data access and conversion code to get the data. For visualizing the data, I use library which is called dygraph. It's a nice small library which is good for drawing time series. dygraph.org. dygraph.com. Here a graph. You can get the data from blobs using HTTP, using XML HTTP request. So you can build application that runs in browser and access data from the Azure as well. Did we solve our problem by visualizing data? Frankly speaking, no. Because if working with NSEP, this is fine. But consider application that wants to plot a map of monthly precipitation all over the Earth. How many data such client needs? The answer is 12 multiplied by 18 multiplied by 22 multiplied by 4. And this is not a small value. A gigabyte and a half. So, to plot just a map precipitation over the globe, our client will need a gigabyte and a half. Okay. This will take significant time, which is, of course, we don't need this gigabyte of data, because on screen we can only view show every tenth of the data element. And chunking storage doesn't provide any solution for this. Another problem with the NSEP. Consider the scenario when you want to plot a graph of temperature over 60 years at some point, at one single point. Here we will need to extract 90 chunks. Each chunk has 2 megabytes of size, so we'll need to extract 180 megabytes just to plot temperature in single line. And you will use only 1 point from this chunk, so 1,000 part of the. This can be potentially solved. For example, you can change the size of chunks, and you can make chunk size for NSEP, let's say 4 by 4 by 5, 4 by 4 by 4 kilobytes. This will make your life easier if you want to display a time series, but this will significantly complicate the situation if you want to display a time slice all over the Earth. You will have to download hundreds of blobs, and we will have to download a lot of data. So the one lesson that should be learned from chunk data storage, that choosing the proper size of the chunk is a difficult problem, which doesn't have a single optimal solution. Depending on your access pattern, chunks of different sizes may behave differently. So here, a performance of reading three-dimensional arrays, chunk three-dimensional arrays in slices parallel to different axes, x, y, and z. And the difference is very significant. It's an order of one magnitude. This graph shows some results from our experiment, reading bytes per second from our chunk storage for different sizes of chunk. And you can see that there is a model, but you can make some assumptions about performance, but the function behave quite interesting. And in one application, this chunk size will work perfectly, while other application will load a lot of unused data and assumption errors. So what to do? And one of the ideas is to, because storage is cheaper, why not to prepare data for different access pattern? From a very simple point of view, this can be storing the same data twice with different chunk sizes, optimized for different access patterns. Sometimes this approach works, but anyway, we'll have problem with Vault Clean. What if we need to build a map of the specification of the Earth in our browser? We can arrange all the data in different chunks, but anyway, one slice has size of 18,000 by 43,000 of elements. So we need to use some filtering, because the resolution of the screen is 100,000 per 1,000, approximately. The first idea that came to mind is just to read every tenth or every hundredth point by latitude and by longitude, and to show not all the data. But this can be dangerous. Visualization is a scientific tool, and as a scientific tool, it should be precise. Scientists won't be happy if we just remove every 9 point of 10. Because in this synthetic example, I have one point which behaves completely different than other ones. And if we subsample our data and just draw 9 points of 10, we will surely, with very high probability, draw this. Sometimes this is critical, sometimes this is not, but we need to provide a precise visualization solution. And the answer is already invented. You see a perfect cloud-based client for big data visualization every time you open a Bing map, or Google map, or Yandex map. Let's see. Maps, Bing.com. I want to use satellite imagery. Yeah, so this is the data, a client that visualize a big data. Because the amount of aerial photography of the Earth is terabytes. How it works? It is very simple and answer is well known. All Earth imagery is organized in a pyramid. On the low level of pyramid, there are a lot of tiles or chunks. They use chunks, chunk-based arrays, which has a resolution about 1 pixel per 1 terabytes a day. But on a high level, these chunks are reduced in size by 2. And each 4 pixels are combined into 1. Then on the next level, again, 4 pixels combined into 1, and so on, so forth, until they get a top level. The top of pyramid has 2 by 2 chunks. This 2 by 2 chunks is less than 1 megabyte, and then you open the maps, you see these 4 chunks. When you zoom closer to the point of interest, you upload more detailed arrays. And this may be a solution for visualizing the precipitation from the WorldClim database. You can build a pyramid of arrays. On each level, the arrays is twice smaller on each dimension than the original one. But then another interesting question appears. You have 4 array elements, and you need to combine them into 1. 4 values combined into 1. What do you do? The main solution just use average. Average of values into 1. Average value. But this is not very good from the Z because if you go to this pyramid, finally you will get an average precipitation as a total. We are called a single value average precipitation over the percentage. And this lose, this present, you lose a very important information, the range, minimum and maximum. So probably when you try to build a pyramid base, you can store minimum and maximum values separate for elements. In one way you store minimum, and another way you store maximum. You will have increase data size twice, but you will keep very important data about layers. And this is another example of how you can prepare your data for visualization, store this data in a storage, and have clients, different clients working with different scenarios to access your data efficiently. So pyramid of tiles and pyramid of the arrays may be a solution. But anyway, in some scenarios, server-side processing is still required. Current slide. Here it is. So, this is our diagram, which is slightly modified. Here we use a line that works together with some auxiliary or helper service running in the cloud. So, first 4 steps are the same. User commands to start experiments, Client invokes some machinery in the cloud. This machinery runs and stores results in the storage. And when client asks for results, client don't go directly to the storage. Instead, client asks some helper service running in the cloud to get the part of the data. The client, then the service accesses the storage, and it accesses the storage inside the cloud, which is much faster. Do you remember our experiment with virtual machine? From my computer, I downloaded one slide set for 12 seconds. In cloud, it serves 300 milliseconds. So if you have a service that provides slides in cloud, you have much better performance on smaller network. But you have to pay for this by hosting a service in the cloud. You pay tens or hundreds of dollars depending on your service for your helper service running in the cloud. But as our experiment with slicing in set data set shows, this will reduce delay for the client in 10 times, which sometimes is worth paying some extra bucks. So there is a diagram of the storage service that we are using inside Fetch Climate project. This storage service performed exactly the same solution, exactly the same problem that we solved with slicing and set data set. We have Asia blob storage. In this Asia blob storage, we store, erase, split it into chunks. Actually, the data that I provide you for your visualization homework is just the same chunks that Fetch Climate uses. But we don't have direct access to this chunk. Instead, we use some data set storage service, API, which works in following manner. If client wants to get some data from the data set storage, first, it looks into SQL database that stores schema information for each variable. Schema information is this one. What is the size of the data? What is the chunk size? How many chunks do we have? And some metadata for providing data transformation units and all other stuff. So from SQL storage, we get schema of the variable. Then client knew, then service knew how many chunks and what part of the chunks he need to get, and he put requests for the chunks into an Asia queue. And there are multiple worker roles, multiple worker services that monitors this queue, and if we want to extract a slice from a chunk, this worker extracts the data and puts the result into response queue. When all the responses are gathered from the queue, the result is sent to an application. So this is a typical architecture of cloud service, which tries to hyperslap data inside the cloud. So this thick arrow is located inside the cloud, and it works quite fast. The drawback I described before. We need to pay for this service. So it may depend on what you need. If you need to store your data and access them with moderate performance, but not very without expenses, just storage, more storage with chunk. If you need to provide fast access to the small portions of chunk, probably you need to deploy this kind of services. Okay, so I believe we are all